Welcome to Beyond the Qubit. Today I have an exciting guest, Ish Dhand from QC Design. And QC Design is a really interesting company to talk to. They develop the design of quantum systems. And with that, they have unique insights what's going on in the quantum world. And I would love to learn all about QC Design today, Dish. So thank you. Welcome that you're here. Can you explain us, so what specifically does QC Design add to the error correction code? What is unique about QC Design that your customers say, well, we want to work with QC Design on error correction code?
So I think what is really unique is the possibility for the customers to study the performance of thousands of physical qubits for any error correction code in the presence of 20 or more hardware imperfections. So this simulation problem is incredibly hard. There are open source simulators which can simulate thousands of physical qubits, but they can only do it for two kinds of errors. So bit flip and erasures, which I mentioned earlier. That's the only thing they can simulate because they're bound by the laws of physics somehow. So this is the so-called Clifford simulators. Or you could have open source simulators which can simulate 20, maybe 50 qubits if you throw a big enough machine at it, and can simulate any imperfection in the system. But our customers care about thousands of physical qubits because you could have thousands of physical qubits per logical qubit, and they care about every imperfection. So what we've built is a set of proprietary simulators, several different simulators at different levels of speed and accuracy that allow the customers to go well beyond what's out there in the open source. Things like leakage, we can simulate very, very accurately for tens of thousands of qubits. There are other imperfections such as, so for simulating leakage, we use our extended poly simulator. For simulating other kinds of imperfections, which is that if your pulse was too long or too short, this is a coherent error, very detrimental to a logical qubit. No other simulator can study this accurately. We have tools which are so-called near Clifford simulations, which can study these. We also had a partnership with NVIDIA, which allows us to basically take that 50 qubit simulator in the open source for simulating anything, for simulating any perfection, and pushing it to 200, 400 physical qubits if you have access to a GPU. So we have this GPU simulator, the near Clifford simulator, and the extended poly simulator can scale to different numbers of qubits, large numbers of qubits, as well as simulate any imperfection that the customers care about.
And given the fact that you said, okay, we do it on site, do you then talk about DGX station from NVIDIA, or is it just the B200 or the B300 GPUs?
You'd be surprised. We used we had a gaming GPU, like one of the 4000 RTX 4000 series, to simulate 400 qubits. Of course, some of the customers do have access to bigger machines, bigger GPUs, and the GPUs keep getting better and bigger and hopefully cheaper every year. So we do think that you can really scale to thousands of qubits with these tools. The hardware is going to get very interesting in the next few years, and I think we are very well positioned to make the tool more useful for our customers.
Yes, so on what are the core items in the technology? So you mentioned the error correction code is very important. Can you maybe summarize? So what I heard from you is that how you differentiate from competition is that you're able to simulate more problems and you're able to simulate more qubits than open source models can do.
Yes.
Why is that? Why can you do that, and why can others not do that?
I think the short answer is that we have our own proprietary algorithms, and we have built the fastest possible CPU and GPU implementations of these algorithms. So that's why our simulators with our proprietary algorithms can simulate these thousands of qubits. There's a lot of deep insights of quantum computing that our team has. We're very fortunate to be able to work with the best people in fault tolerance and quantum hardware and quantum software. These insights have been boiled into algorithms and implementations. So that's the simulators. But the simulators by themselves are not enough for it to be a product that our customers can use day in and day out. And actually, around that, we've built a library of error correction codes, control methods, decoders, so library of architectures, and library of error models. So every architecture, every error correction code that a hardware company has published about, so open publications. We've put that into production quality code. Every error model that hardware teams have published from academia, from industry, it's available for our customers to mix and match. So this library of codes and
How does that work? So for example, Riverlane comes up with a new error correction code, or Google or Microsoft. How can you put it in your library? How does that work? And does Riverlane allow you to put it in your library? Or is it proprietary to Riverlane? Or is there also an incentive for Riverlane that it is in your library?
Yeah, so often I would say all major error correction codes in literature, they were first published in academic groups. These were publications rather than patents. And if these error correction codes were patented, what is patented is the possibility to realize these error correction codes on hardware. A device that runs these error correction codes is patented, but the simulation of these codes is not something that's patented. Yeah.
Oh, wow, that's interesting.
And it's not some crazy loophole. It's just that, I can always study an algorithm. I can study a method with whatever tools are at my disposal. It might be that a patent prevents me from building that particular code. So that's, I think, maybe kind of the foundation, that simulation is never is maybe a strong word, but I would say, yeah, I think with high confidence I can say simulation is never blocked by patents.
So maybe to summarize, so for Riverlane, they are okay if the customers simulate it, the error correction, but when they start to use it in real products on real hardware, then they have to pay for it. But for the design, for the simulation, they're okay, because for them the benefit is really when people are going to use it.
Yeah, I do want to add a fine print there. I
think
Riverlane's focus is really on decoding. It's really on the algorithm to find and correct the error, and have implementations of these in silicon, like the best possible implementations through ASICs and so on. And I believe that the business model, at least from the publicly available material, is to sell this chip, which is an instantiation of their decoding algorithms. So it's really a hardware company selling silicon chips that will control every quantum computer. And I think they're doing incredible work here. In terms of what you're describing, new error correction codes, I believe that's more an ARM way of thinking, that I would make an architecture and then license the architecture. I think there are several companies now that are starting to move towards this. For instance, there is Parity Quantum Computing based in Innsbruck, so Austria and Germany, and Iceberg Quantum, that's based in Australia. And they are moving towards this IP licensing approach. So I do think that there are companies coming up who have patented certain ways of doing fault-tolerant quantum computing and who are providing licenses of these patents. I think maybe the more common thing that we could come across is suppose a hardware company has developed a new error correction code, and suppose they've patented the use of this error correction code to correct errors on their hardware. If there is a competitor of theirs, the competitor is not prevented from studying the performance of this code. Placket helps them do this. The competitor is not prevented, it's not blocked. And I think that's kind of the whole point of IP and patents, is the competitor can build on top of what this company has built, can completely propose new error correction codes, maybe based on the learnings from this one, maybe not. And with all of these things, so coming up with improvements or replacements to existing error correction codes requires a tool like Placket. So that's what our customers use it for coming up with completely new architectures. Of course, to come up with the new architectures, it is helpful to study what's out there in the literature, and what better way to study than ultimate production quality software with which they can simulate the feasibility and the tolerances in a matter of minutes.
And can you clarify one thing for me? Is your product, the design, is it predominantly in software on the error correction code, or is it also like Synopsys and Cadence? They also help with the design of the hardware. So what exactly does your design optimize for? What elements? Is it like the silicon or the chip? Is it like the input output? Is it the software on the chip? Is it Is it the error correction code? What are the elements that you cover within QC design?
Yeah, thanks for asking. I do think that this is it's hard to grasp where the software comes in. How we think about it is that our customers from all different platforms use their own tools to design physical qubits. So on a superconducting chip, you could have specific Josephson junctions, which are arranged in a certain manner. You could have on a photonic quantum computer waveguides that have a certain width and are arranged in a certain manner on a silicon chip. Or you could have trapped ions from a company like Coherent, who would suspend these atoms in a particular arrangement and then move some other atoms in some other arrangement. For studying the physical qubits and the error on a single physical qubit, our customers have their own tools. So for superconducting qubits, photonic qubits, spin qubits, these tools are standard cadence and synopsis and ANSYS EDA tools. For neutral atoms, trapped ions, these are atomic optical simulations. QC design picks up where our customers' physical qubit design tools leave off. So once our customers have a physical qubit design, from there, they want to figure out how to connect these physical qubits. Again, for a superconducting qubit, you could connect it in many different ways, depending upon the error correction code. And this
what do you mean? What do you mean with connecting? Do you mean from superconducting to ion trapped? Or do you mean from superconducting to one chip to another chip, so forming clusters? Or do you mean you have one chip with multiple gates and you want to form a logical qubit out of physical qubits?
All of these. So the simplest,
And are that separate products, or is it just one product that enables you to do multiple?
It's one product. It's one product. Okay. So the simplest, and here I don't mean easiest, the simplest design problem is within a chip, you have physical qubits. Do you arrange it in a square lattice? Do you try to put together two different chips that have some non-local connectivity? Do you have a hexagonal lattice, a triangular lattice? And when you act pulses on qubits in this lattice, what's the order in which to apply the pulses, how long or short should, or how intense these pulses should be? All of this is on a single chip. And all of this is necessary for building a logical qubit on one chip. From here, of course, you want to scale up. You want to put many chips together, or you want to connect, for instance, ions that are in different traps connected to each other through photonic interconnects. Here, what you have is, at an abstract level, different error models acting within the ions, within the separate traps. So 50 qubits here have low errors when they talk to each other. 50 qubits there have low errors when they talk to each other. But then when they talk to qubits across traps, then there's a very high error rate or a very different kind of an error model. Actually, it could be optical loss. With superconducting qubits, if you're putting two chips next to each other at the interfaces, you see very different error models. So if you have a tool which can study arbitrary error models on arbitrary hardware platforms, then you know how to lay out physical qubits on a chip, how to connect chips together, or basically connect chips together by placing them next to each other or by connecting them through photonic interconnects and so on. It's a vast design space. So we have some customers looking at how to do distributed quantum computing, where some customers looking at imperfections that arise from interfaces of chips, and some customers looking at, okay, within a chip, how do I best lay out my physical qubits at an abstract level? Of course, then afterwards, they would use tools from cadence or synopsis to actually lay out the very final structures that are then fabricated on the chip.
Okay. Thank you. Thank you for clarifying. What about error decoding? Is that important for QC design?
So it's something where we want our customers to be able to know what is the impact of error decoding. Let me just take a step back. So decoding is also, so it's the process of finding where the errors occurred on the system and then correcting these errors. Finding where the errors occurred is actually very hard. Again, quantum is different from classical. In classical, you have these 5 bits, 5, 5, 5, 5, 5, and then you just take one bit and you measure it. And hey, you know whether it was 5 or did it flip to a 4. In quantum, if you do this, then you lose your information. So this is the so-called measurement problem. If I have a qubit, some entangled superposition, whatever, you measure it, you've destroyed all the information in the qubit.
And that's because the state collapse.
This is exactly because the state collapsed. Exactly. That's also the Schrödinger cat experiment or thought experiment that people talk about. But then how do you get around it? You have these. So I spoke about data qubits, which are some physical qubits. You have these ancillary qubits, ancilla qubits that are sitting next to these data qubits. They talk to the data qubits. They figure out which of the data qubits could possibly have had an error. And then you measure the ancilla qubits. So you have some indirect set of symptoms. They literally call it a syndrome. So you get a set of symptoms of, okay, well, we are seeing that this ancilla qubit and this ancilla qubit have a funny result, which is unexpected. Then from these measurements, you want to know, okay, which of the data qubits actually had an error? This reverse problem, you have to infer where the errors occurred and what these errors were. Solving the inverse problem is decoding. And it has to be done incredibly fast, so that you don't have basically too much measurement to store, because a large-scale quantum computer will be producing more data than Netflix, all of Netflix, and you want to be able to process all of this data very quickly and then use this processed correction and apply the correction on your qubits. So that's the decoding problem. You could have optimal decoders. You could have decoders which are going to give you the best possible correction. So from the set of measurements that you perform to the correction which should be applied on the computer, there are decoders which could give you the optimal performance, but these are exponentially hard. These are not realistic at all beyond 5 to 10 qubits. And on the other side, you have much faster decoding algorithms, which will give you terrible corrections, which will overall lead to an increase in the number of physical qubits you need per logical qubit. So the decoder is also very important in understanding the overhead. And we help our customers try out all the different decoders available in literature, or maybe develop their own and plug it into the software. And by studying this, they know, okay, what's the impact of the decoding algorithm on their physical to logical overheads.
I think it's fascinating. So thank you for explaining it. Qubit definitions, can you explain how that plays a role for QC design? And I mean, with qubit definition, I mean how qubit levels are defined from hardware.
Yeah. So I think we were already talking in this direction earlier. So different hardware platforms use different definitions of qubits. So for photonics, you use pulses of light. And if you have two waveguides, or think about it as two optical fibers, waveguides would be the analog of the optical fiber on a chip. If the pulse is in this waveguide, that's state 0. If the pulse is in this waveguide, that's state 1. You could have superpositions of the pulse being sometimes here, sometimes here. That is the qubit in photonics, or one kind of qubit in photonics. You could have another kind of qubit in photonics, which is being pursued by Xanadu. I don't think I can explain it in words very easily. Very complicated states of light. You could have qubits in atoms. So atoms, of course, have electronic levels, and these electronic levels have different energies, and you could have the electron or the atom being in different energy states or superpositions of these energy states. Which energy states you choose matter, because different energy states could lead to different levels of leakage, could lead to different requirements of what kind of lasers are used to control these atoms. And therefore, these different definitions of qubits could have very different error rates acting on these atoms. So the result is that, again, it becomes this insanely broad design space where a hardware engineer has to think very carefully about all the trade-offs. Should I define my qubits like so? Or should I use this other flavor of qubits, which is maybe much harder to control, but potentially has much lower overheads? So these kind of trade-offs, the engineers are always thinking about, and our job is to help them with it.
How do you simulate this for your customers?
Yeah, so our customers usually have their own in-house tools for simulating different realizations on the hardware, and their tools will give them different error parameters. And different error parameters are what they would put into Pluckit. And then they would see, well, this kind of a design of a qubit has error parameters that are overall worse for the logical qubit than this other design of a qubit. And the result is that they can make an informed choice.
So they have their own measurements and they
Yes.
put it in their systems, and it stays locally on their on-site. And then
Very important.
Okay. Thank you for clarifying. The last one on the technology, sorry for asking all those basic questions, but I think it's important to understand. Qubit control. Which pulse sequences are used to control the qubits? And how does the simulation work?
Yeah. Overall, the problem is to figure out how to control the qubits. Normally, control the qubits means if you want to apply a gate on a single qubit, you would zap it with, so let's talk about matter qubits. So there's either photonic qubits and every other kind of qubits, which is matter qubits. Matter qubits are chunks of matter, which could be atoms. It could be some kind of structure on a superconducting chip, which is a superconducting qubit. And you would zap these qubits with electromagnetic radiation. You would zap an atom with a laser, or you would zap a superconducting qubit with a microwave pulse. What kind of pulse to apply? How long should this pulse be? How intense should it be? How strong should it be? This is the question. And there's a big trade-off in the whole control space. So for instance, if you have two qubits that you want to control, like act a gate between as a part of the error correction cycle, if you apply a very short pulse, the gate is crappy. Then you get a gate which has not 4 nines of fidelity, but only 2 nines of fidelity, suppose. So shorter pulse is worse for 2-qubit gate fidelity. But if you apply a longer pulse, this means that all the other qubits are sitting around doing nothing, and they are gathering errors by just sitting around doing nothing. So this idling error from decoherence is also a problem. So if you have it too long, then every other qubit has a lot of error. If you have it too short, then this pair of qubits has a lot of error. What's the sweet spot? So understanding such trade-offs is very important to the customers. And with that, with Placket, they can do this. How can they do this with Placket? If they would choose a particular sequence of pulses, those sequences of pulses would translate into a set of errors, a set of different error parameters. So the idling error is this much, and the 2-qubit gate error is this much, the leakage error rates are this much as a result of that sequence of pulses. And then they can study the overheads for this sequence of pulses. They change the sequence of pulses, maybe the overhead goes up, maybe it goes down, which would be awesome. So that's how they use Placket to find the best way to control the qubits.
I think it's a very powerful solution for your customers to simulate those problems. Okay, quantum error correction is often seen as a bottleneck for scaling. What makes QC design approach unique compared to surface codes or other established schedules?
Yeah, we see ourselves really as a tools company. We provide this one tool that our customers use to come up with the best approach. So we're not competing with surface codes. On the other hand, I think many of our customers do start by simulating surface codes. We allow them to go well beyond surface codes, to look at every error correction code people have published in literature and design their own error correction codes. And basically, as a result, have the best architectures.
Okay. So what you're saying is that you are more the interface. So you allow them to compare all the specific codes and not one individual.
Yes.
Can you explain what hardware-tailored error correction means in practice?
Absolutely. The whole process of understanding the impact of realistic imperfections on the user's hardware, on our customer's hardware for their particular architectures. It's the starting point. And if you would come up with the best architecture for somebody else's hardware imperfections, that's not optimal for a quantum hardware company. They know their error models today. They know their error models 3 years, 5 years down the line. And for these error models and parameters, what's the best architecture to design? What's the architecture that has the lowest footprint? What's the architecture that needs the least engineering effort, time, money to build? So that's what we mean, that QC design helps customers come up with the best hardware-tailored architectures.
Okay. You alluded already a little bit to it, but for what technology, quantum technologies, can QC design, the simulation software, be used? Or which one is it not possible?
We're already working with customers from 5 out of the 6 main hardware platforms, and actually we think a 6th one is coming very soon as well. So Placket is useful for every hardware platform out there. We worked very hard to make sure that error models from all the hardware platforms are in there. We've worked very hard to make sure that the simulation framework itself is agnostic to whether photonic qubits, being simulated or matter-based quantum computing. And the result is basically that every quantum hardware company across any platform finds the tool useful.
Wow, that's quite powerful. How do you integrate with hardware partners like superconducting, trapped ion, or photonic qubits?
The interface looks very simple. So it's really that the tool is provided to them with a simple annual subscription based on the number of users in the org, based on the number of architects and hardware engineers who are using the tool to study their architectures. And then from there, it's basically they get license key and then they can install the software. It sits on their device like a Python package, like any other Python package that they use for the rest of their research. So if they're using open source Python tools or if they're using their own in-house Python tools, then Pluckett sits right alongside these tools in a seamless way. And they can have all of these tools talk to each other and basically use that to design the architectures.
What are the two breakthroughs that really accelerated QC design the last 2 years?
The product and the market. Yeah. So we went, as I mentioned, so we really feel like we've hit product market fit in these last 6 months. And there were really two aspects of what we were doing or what the industry was doing that made a huge difference. In terms of the product, I think we were able to learn from the customers that to them it's really important to simulate all of these 20 imperfections. I keep saying 20. In principle, it could be 20 for each platform. It could be any number of imperfections. But it's crucial for the customers to simulate arbitrary hardware imperfections. And internally in the team, we had a breakthrough where we came up with algorithms to simulate any of these imperfections. These algorithms are based on Clifford simulations, the idea that you can have very fast simulations of the computational states of the 2 qubit levels. And on top of that, if you add a lot of classical labels, then you can basically simulate everything very, very fast with thousands of qubits. So this was maybe one breakthrough on the technology side, very, very motivated by the customer's problem. I think in terms of acceleration, the other aspect that we see around us is that in the last year or so, there's been so much going on in the market. Fault-tolerant quantum computing is now mainstream. I would say now every serious quantum computing company is a fault-tolerant quantum computing company. Many, many serious players have roadmaps to hundreds of logical qubits in 3 to 5 years, which means that internally all of these companies have massive efforts which are just taking off right now to design these qubits. So for us, this is a great time to bring the product to these customers because then they don't need to invest the tens of millions that they need to invest to build and maintain the software in-house. They can just buy these annual subscriptions from us and move fast towards the goal of designing and building fault-tolerant quantum computers.
What are the most important building blocks, the technology building blocks for QC design?
It's absolutely these proprietary simulators. That's the core IP for us. These simulators that enable simulating arbitrary imperfections on thousands of physical qubits. And along with that, it's the libraries of all of error correction, basically. We've taken every error correction code, decoder, error model that's relevant, that's published in literature and put it into the software. So this library, along with our proprietary simulators, that makes it a complete product. That makes it a product that our customers can use every day and it accelerates their workflows.
How can you help to scale your customers towards 100 logical qubits and 2000 logical qubits? And can you explain it up by splitting up the improvements in the scale up, so more qubits per chip, the scale out, more clusters, and the error correction ratio? And of course, it depends per technology. So each technology has each individual.
That's absolutely the goal for us, helping our customers get to hundreds of logical qubits and eventually thousands of logical qubits with the least possible risk, and of course, as fast as possible. And how we help them with this is the hardware side is working as fast as possible anyway. First, we enable the architects, the error correction researchers, to come up with the best error correction codes. So we mentioned hardware-aware error correction, hardware-aware architectures. So what's the best error correction code that corrects for all the errors that arise in their system, as opposed to an abstract superconducting system, for instance? So good error correction codes can cut the cost of a logical qubit by a factor of 10. Maybe there's another factor of 10 still in there. So that's one aspect. But the other aspect is also very important, which is that with Placket, our customers know which of the many imperfections in the system is having the maximum impact on their architecture. So it could be that they think that the erasure rate is very high and the leakage rate is very low, but it could happen, for instance, that leakage is having much worse an impact on the logical qubits, on the overheads, than erasures. Instead of devoting many so a lot of engineering effort, many engineering years towards improving erasures, then they could devote that towards improving leakage, which would then cut the cost of building a quantum computer. So in the end, this also translates not just to a single chip, but also to clusters of chips, so chips talking to each other. Could also translate to chips that are delocalized, so far away from each other and talking to each other through some interconnects. The outcome for our customers is always the same. They can come up with the best, they can come up with ways to have a fault-tolerant quantum computer with hundreds or thousands of qubits with the least possible amount of hardware, engineering effort, time, money, all of that.
Okay, thank you, that's clear. What are the key trade-offs between code efficiency, hardware overhead, and logical fidelity?
Yes, this is a very nuanced problem within quantum error correction. Logical fidelity is, I would say, a requirement. A user wants to run a molecular simulation. So an end user of our customers. So a pharmaceutical company wants to devise a new drug using a quantum computer made by one of our customers. They will say, okay, we need algorithms, and the best algorithms today, you need to run 10 billion gates on the qubits to implement this algorithm for our drug. This imposes a requirement on the logical fidelity. The requirement would roughly be 1 in 100 billion, so it would be 10 times or so something along these lines. If you want to be able to implement n number of gates, you want error rates that are 1 over n or 1 over 10 times n in that. Okay, so based on the algorithm, based on the requirement, our customers know what logical fidelity they need to get to. Suppose it's this 100 billion, one part in 100 billion number. Now, for every error correction code, there will be a different number of, for every error correction code, for every error set of error parameters in the system, there'll be a different number of physical qubits needed to get to this very, very low level of logical errors, or this very high level of logical fidelity. Our customers want to find that particular architecture which has the lowest overhead, the lowest number of physical qubits needed to get to these logical fidelities. So that's kind of the complicated interplay between these three, between logical fidelity, the code efficiency, as well as the overhead.
Okay, thank you. What role do AI-related optimization and simulation play in your pipeline?
This is something we're really excited about for the future. We want our customers to be able to really use all the tools at their disposal to come up with the best architectures, whether it is the smartest error correction architects and researchers and hardware engineers, or the smartest AI model that help these researchers and engineers working in these companies. So Placket is actually a tool which is insanely good at this. We did not build it for this, but actually it's really, really good. Placket contains all of error correction in a form that AI agents can really readily absorb and iterate on, as well as it's the ultimate validation sandbox. It's a tool where an architecture that an AI agent devises, that architecture can be validated. Does it actually work? And it's a real world validation because we can simulate any imperfection. So with this knowledge base of all of error correction and with this overall validation sandbox, then AI agents can come up with the optimal architectures. Of course, we designed it for humans, but it also ends up that the AI agent friends of the human users can also use it to come up with the best possible architectures.
Mhm. Okay. How do you benchmark progress towards fault-tolerant quantum computers, and what metrics matter most?
Oh, that's a hard question. That's a hard question.
Is there one metric that matters more than other? Because of course you have to see it in combination with everything, but is there one that you say, well,
I guess maybe one that could matter is how expensive is it today? And how expensive is it in 3 to 5 years to build a large-scale, useful fault-tolerant quantum computer? I would say right now, if you would ask, it's the cost of building a fault-tolerant quantum computer, a truly useful fault-tolerant quantum computer, is infinite. Because no amount of money that you throw on it, throw on the problem, will get you to the hardware, to the error rates that you need to build a fault-tolerant quantum computer. Okay, maybe some of the hardware companies already have hardware that's clean enough for this and scalable enough. But I do think that all platforms still have challenges in basically getting towards the large number of physical qubits they need to build a useful quantum computer. What does this number look like in 3 years? What does the number look like in 5 years? Hopefully it's smaller than infinite. Hopefully it's less than $1 billion. Wouldn't it be awesome if it's several tens of millions? So that number depends upon a lot of things. That number depends first and foremost on the number of physical qubits per logical qubit. But it also depends upon how clean these physical qubits need to be. A physical qubit with 4 nines of fidelity will necessarily need much more engineering effort and time and so on as compared to something that only has 3 nines of fidelity. So I would say that's the number to work on. That's the number the whole industry is working on. And hopefully we can play a small part in bringing that number down. First, from infinity to non-infinity to a finite number. And then second, from several billions of dollars to hopefully several tens of millions of dollars in the next 3 to 5 years.
And what is the trade-off there? So is it more important that the costs are coming down, or is it also the amount of nines?
The amount of nines help bring the cost down.
Okay.
So, but maybe you don't want to go to 6 nines. Maybe you don't want to put in insane amounts of engineering effort to make the physical qubits very clean. Maybe that engineering effort is better spent in solving scaling up problems. So for instance, if you have a 50 qubit ion trap and you can't go beyond 50 qubits, it doesn't help if you keep making these 50 qubits cleaner and cleaner. You want to solve the scaling problem. How do you go from 50 to 500, 5,000, 5 million? So in the end, one needs to figure out what's the most efficient way. I guess money is one way of quantifying this. What's the most cost efficient way of building a useful quantum computer?
Okay, that's clear. Ish, over the next 3 to 5 years, what are the key metrics that you track, or that I should track, or that investors should track to demonstrate progress?
I think this is a very interesting question, and this question changes. So the answer to this question changes over time, I would say. Last year, I think many people were tracking the number of physical qubits. I think now it's very good to see that many people are tracking number of logical qubits, but not all logical qubits are the same. So one thing to track is what you already mentioned, logical fidelity. This is connected to how many gates a logical qubit can implement. So if a logical qubit can implement 1 billion gates without losing all the information, this is a very high logical fidelity. If a logical qubit can implement 5 gates before it becomes basically garbage, then this is very low fidelity. So I think it's really important to track the quality, this fidelity, and the quantity of logical qubits in the next 3 to 5 years. So many companies have roadmaps to get to 100 logical qubits. I am cheering for a world where these hundreds of logical qubits have very, very high logical fidelity. These hundreds of logical qubits can implement very deep algorithms with millions, maybe billions of gates acting on these logical qubits.
And I understand that, but that's for the whole market overall, but specifically for QC design. What are the metrics that investors should pay attention to?
Okay, I do want to answer your question, but before that, I want to answer a slightly different question of
Yeah.
what are the metric that matters to me? What are the metrics that matter to the team? And I think really the metric is, can we bend the arc of fault-tolerant quantum computing? Through our tools, can our customers cut the cost of building a fault-tolerant quantum computer by a factor of 10? Can they cut it by a factor of 100? Or can these customers get to hundreds of logical qubits sooner? I think that's the thing that matters most. Are we helping our customers build something awesome? So that's kind of the thing that matters the most for us. I would say we are in a very good business model, very, very much inspired from electronic design automation. It's a very sticky business. It's a business which continues to add value to the customers, and the customers continue to work with the providers. For instance, companies like Intel, Apple, Samsung, of course, as you very well know, they are spending hundreds of millions on EDA tools, not because they couldn't do it themselves, but just it wouldn't make sense for them to do it themselves. It'd be much more expensive. So we expect that as our customers build something awesome, can get to billions of dollars of revenue from building and selling these fault-tolerant quantum computers, that a part of the value also comes to QC design. And so the investors should be tracking revenues. They should be tracking how fast our revenues are growing, and in particular, how fast quantum computing as a field is growing. Because if we continue to lead in quantum design automation, if we are able to become the cadence and synopsis of quantum computing, then we do imagine a world where a few % of the entire quantum computing revenue could also be QC Design's revenue. Just like Cadence and Synopsys and others capture 3 to 5% of semicon revenue.
I think that's a very powerful metric to look at. And that brings a lot of fantasy. What I would love to know is can you walk me a little bit about the ecosystem? And can you talk me through, okay, what are the main partnerships that you have? Maybe university or key suppliers or key customers or...
I think in terms of the main partners we have, it's really the early customers, the customers who are working with the product or who started working with the product even when it had rough edges. Now it's a much more mature product. So I think that makes a huge difference. The feedback allows us to make the product more useful for everyone. That's the, I would say, 99% of the effort for us. Then that's 99% of the value added to the product. Other than that, I think really a fault-tolerant quantum computer would not exist in vacuum. There would be all kinds of other tools needed to make it work, whether it's companies that would be responsible for controlling the qubits. So we spoke about kind of choosing what's the best control sequence, but then in reality, what does that translate to in terms of real microwave engineering and so on, or companies that are building decoders, or companies that would be building compilers on how circuits are implemented. So all of these players would impact fault tolerance design. And we are looking forward to being more and more a part of the full fault-tolerant ecosystem. It's an ecosystem which is very, very early. It's only now that the entire industry is realizing how the different parts fit together. And I think over time, there will be strong and very productive partnerships between all of these players. I think Semicon is the best example, with so many incredibly strong partnerships across all different players, the hardware vendors like Samsung to the display manufacturers, all of these. So that's the world that we see happening in 3 to 5 years.
And Ish, what are the main relationships of universities? Are there certain ones that you can highlight?
Yes. For us, I think being able to work with universities is a great opportunity because, firstly, it really tests the tool. I think, of course, our customers are also our quantum hardware customers are also at the edge of what's humanly possible, but also in terms of research. We have partnerships already with a couple of universities. They are using Placket to design new error correction codes. And recently, there was a master's thesis, in fact, where Placket was used to develop a completely new way of doing error correction with photonics, and which will be published in the coming months. So I can't share more information about it. But this kind of validation is incredibly helpful for us because with this, we know, okay, this is a tool that is at the bleeding edge. And what do we need to do to keep it that way? There's also another interesting point that happens here. We do see something cool emerging for us, which is that PhD students using Placket during their PhDs, well, they would move to the industry and want to keep using the tool because they know how awesome it is and how much value it adds. So I think for us, this makes sure that the pipeline gets a bit broader. This makes sure that the tool stays sticky over the long run.
And how do you distribute it? Do you distribute it freely to all universities globally?
It is a different kind of pricing model. So very similar to how ANSYS tools are cheaper for university groups than they are for companies because, well, there's different kinds of value coming to both and different value coming to us from both of these partnerships. So it's different pricing for academic groups versus selling to commercial to quantum hardware companies.
Okay, fair enough. Can you walk us through the business momentum? So why is QC design real? And what is the traction that you have with your main customers? You mentioned already, okay, the last 2 years we moved to 6 paying customers or 5 paying customers. What is the momentum and what gets you excited?
Well, the part that gets us excited is really helping these customers build something awesome. So I think that is irrespective of the revenues. I think it's very cool that 6 months back we went from 0 revenues to now last quarter 5 paying pilots, revenue of the order of $200,000. These 5 paying pilots were in the range of 2 to 6 months. Very different value to the different customers, all customers at different ranges. And now we're moving to subscriptions. And yeah, I have to say, like every other startup, we go to our investors and go to future potential investors and we tell them, hey, we are projecting X amount of revenue by the end of the year and X by the end of next year. We've been doing that for the last few months. And every single time we've gone back to them, these projections are now increasing. So we've taken those projections, beat these projections by a factor of 2. And then the new projections that we have are so much higher. And we keep on beating these projections. I think this is really what product market fit looks like. We do see customers finding true value from the product and more customers coming in. We expect to get to already $1 million in ARR in the coming months and scaling to maybe 10 million or so in the next 2 years. And I think for us, this is awesome because all of our customers are startups. They would not spend money lightly. This really means that they're finding true value. This means that this tool is helping them get to something awesome.
And Ish, when do you expect what needs to happen for you that your conviction in QC design goes bananas, that it goes really high? You say, okay, well, now what are you looking for? You say, well, for the coming 5 years, if this particular thing happens, then my conviction really is going up. What would it be?
It's about bending the arc of fault tolerance. It's really about helping our customers make useful fault-tolerant quantum computers that'll change the world. So can we help our customers do this a year or 2 sooner than they would have otherwise done it? Can we help them do this with 1 zero less in the bill of materials than otherwise? So if we see this happening, then I think then we've accomplished our mission, and this is something that's really added value to the world.
Okay, maybe to conclude, could you summarize why investors should pay attention to this QC design?
Yeah, I would say investing in QC design is investing in the future of quantum computing, which is the future of computing. So QC design will win no matter which hardware platform or platforms wins the race to fault tolerance. QC design is taking off right now, and we have something which is truly useful for the industry. So we are in a position where we're quite confident that in 3 to 5 years from now, QC design will be one of the big players, will be the cadence or synopsis of quantum computing, and then quantum computing will be the future of computing. So yeah, that's why I think investors should pay attention to this.